Welcome back. Today we're doing a deep dive into NASA's Deep Space Optical Communications, or DSOC.
Right.
This thing is, well, it's a game changer. It basically took deep space communication from, slow dial-up
Oh, yeah, pretty much.
to something that looks a lot more like the fiber optic internet you might have at home. So we're going to unpack the record set and just how they pulled this off.
And it's really not hyperbole to say this redraws the map for exploring Mars and, well, everywhere else. The big win here is showing definitively that you can send and receive laser-encoded data reliably over, huge interplanetary distances.
Okay.
They just finished the mission, actually. Got a final signal during the 65th pass from, get this, 218 million miles away.
218 million miles. That's
Okay.
hard to even picture, but let's give that some context. What are we normally talking about with traditional radio frequency RF signals from that far out, speed-wise?
Kilobits? Maybe. On a good day?
Kilobit.
RF is super reliable, which is why we use it. But yeah, the bandwidth for really distant probes is tiny. Kilobits per second. Now, DSOC, they downlink data successfully from 307 million miles.
Whoa, okay.
That was back on December 3rd, 2024. And that's farther than the average Earth-Mars distance.
Yeah.
Set a new record for optocomms distance. And over the whole mission, they pulled down 13.6 terabits of data.
Terabits. Okay, that's the volume and distance. Let's talk speed. You mentioned fiber optics. Did they really hit those kinds of rates? Was it stable?
They really did.
Yeah.
December 11th, 2023, that was the peak. They streamed ultra-high-def video back to Earth at 267 megabits per second.
267 megs.
Yep. And that wasn't even from the farthest point. That specific test was from about 19 million miles out. Still, that's like 80 times the Earth-Moon distance.
Okay.
So yeah, it proved optical isn't just a lab experiment. It works for real high-bandwidth needs in space.
Incredible. But the engineering, hitting a receiver on Earth from that far while everything's moving, how do you even manage the pointing?
Yeah, the pointing. That's fascinating. The spacecraft Psyche, it couldn't just guess where Earth was precisely enough. It needed help.
Like a guide beam.
Exactly. A powerful 3-kilowatt uplink laser beacon from JPL's Table Mountain facility is shown up towards Psyche, basically saying, here I am.
Okay.
And that gave Psyche's transceiver the target it needed to aim its own much weaker downlink laser right back at the ground stations.
And that return beam after millions of miles must be incredibly faint. Just a few photons, right? How did
Yeah.
they catch enough of them to make sense of the data?
Right, you need a really big bucket to catch those raindrops. That's where the 200-inch Hale telescope at Caltech's Palomar Observatory came in. That was the main downlink station.
A big one.
The really big one. Its huge mirror collected as much of that faint laser light as possible, channeling it to super-sensitive detectors. That's like the ultimate light-gathering eye.
Makes sense. And you always need backup redundancy. Did they just rely on Palomar?
No, and that's smart engineering, like you said. They tested two key things for robustness. First, arraying. They linked Palomar with a smaller 1-meter telescope, also at Table Mountain.
So making a bigger virtual telescope.
Exactly. It boosts the signal collection. Second, and this is really interesting for the future, they tested an experimental antenna at Goldstone. It's a hybrid antenna.
Hybrid, meaning?
Meaning it could receive both the traditional RF signals and the new optical laser signals from Psyche at the same time, using the same dish structure.
Ah, okay. So built-in backup for different conditions.
Precisely. Ensures you can maintain a link even if, say, clouds interfere with the laser temporarily. You've still got RF.
So pulling this all together, what's the big takeaway for NASA's plans? Astronauts on the moon, eventually Mars.
It means the data fire hose is now possible. NASA sees this optical tech as crucial for augmenting, bolstering the existing RF network.
So not replacing RF, but adding capacity.
Right. Think high-def video streams from Mars rovers or, massive data sets from complex instruments sent back almost in real time, things that were just pipe dreams with RF alone. This really enables that next golden age of exploration they talk about.
Okay, so here's something to think about then. They proved they could combine optical and radio with that hybrid antenna and the arraying. Does this mean future deep space networks will just build that redundancy in from the start? Guaranteeing we always have a connection across the solar system, no matter what space weather or Earth's atmosphere throws at us?
That's a really good question to ponder. Seems likely, doesn't it?
Something for you to mull over until our next deep dive.